Next speaker is Iraj Kalantari from Western Illinois. There you go.
I think brevity is good. By media, I mean things like polynomiography and other software. By play and expression, I mean what our colleagues did earlier today before lunch. By curiosity, neurological stuff and the interest, we know what we mean by learning. We've met Batman's talk. I'm done. Little earlier dinner, that was in promotion of. I'd like to tell you a little bit about where I am coming from. I am in the math department of a university which is about 12,000 big. It's a state comprehensive university, which means we get a lot of the students whose ACTs are all the way from 18 to, say, 28, plus or minus few at the endpoints. We have about 100 math majors. These 12,000 students, we have maybe about 2,000 to 3,000 students coming in as a freshman class, and over 50% of them, this is now 54, 55% presently, and it has gone from 32%, say just about 6 years ago. That percentage of people need to take intermediate algebra when they come to university. And of course we all know that's a no credit course. We all know they hate it. They find themselves in a place they'd rather not be. They're paying for a course, they don't know the stuff, they think they do, and it is indeed a undesirable situation. Obviously, at a department like mine, where we used to be a normal school, half of our students are majoring in mathematics education. They want to be teachers, and half of them are standard math majors. Now, because we have half of our students who intend to become high school teachers, we have activities such as ICTM. Some of you know that is Illinois version of Council of Teachers of Mathematics. And we have grants, and we do a program called Girls Plus Math. I shall come back to that in a little while. The challenges that face our students are not unfamiliar to any of you who taught freshmen. They come, and as I was saying, they must take a mathematics course as part of the curriculum in general education. They are underprepared, so they end up needing intermediate algebra, and then after that they need another course from us in mathematics, which is essentially applied algebra, and after that yet they need another course. This is, which is a general education course, maybe math for poets, math for artists and the like. Now that's for people who are not following sciences nor following business. So it is 3 courses to take in mathematics, and it's a great challenge, and we are continually finding ourselves that hard place between trying to make the students satisfied and yet maintaining standards, trying to bring out in them the best that they can absorb, yet actually doing something that is new and challenging for them. The importance of cooperation I'm referring to here is in the whole fabric of K through 14 or K through 12. So I'm trying to reach education-oriented minds present here and elsewhere through that important cooperation. Now, the challenges that are facing us, and I guess I'm speaking of the ones that are facing me when I teach myself, and I believe my colleagues do, I have sort of summarized caricaturishly here. Learning concepts, these things reside in the imagination. Then there is vocabulary, which obviously has to be connected to meaning and a sense of semantics. And then, of course, we expect of them to do technical stuff, which resides in syntax. And of course, the difficulty is when we teach mathematics to students, whether it's intermediate algebra, college algebra, or somewhere in between, often we're trying to do these 3 things simultaneously. Motivated student, the student who has imagination and sort of a good language of sciences and a curious mind, can handle these better. But most ordinary students the center of mass of the students cannot do these things simultaneously. A bit more formally speaking, I think what I'm mentioning here for you is that, again, experience of all math teachers, every now and then we have a new plateau. And this new plateau is difficult for students to absorb. We're talking about functions when it is in intermediate algebra, perhaps. We're talking sometimes about the concept of limit if you're doing calculus, probability, conditional probability. We are always hitting new material, and those are what I'm referring to as plateaus. We need to be able to abstract, and abstraction is a very difficult thing to imagine. I needn't explain that to you. And there is, of course, the shift from static to dynamics, which is always a critical factor. Now, one of the examples of these, the static and dynamic, I'll come to in a second. But what again is some examples for all of us to remember or to imagine is that the challenge is to learn the subject while learning the vocabulary of that language. And I imagine that most of you, certainly myself, I have experienced some of these things that I've been a bit more successful in than others of these things. But we're always trying to learn something and learn this vocabulary at the same time. We're thrown into the throw of things simultaneously. And of course what we do is we resort to, it's good for you, you must try it, and the road method. Now, a few examples to sort of see what I'm referring to, at least in my terminology. Some of it may not be standard even for those of you who are in education, because I am not in that area by training. When we're trying to teach functions, for example, we all know that it is good to try to refer to what happens to f of x plus c and f of x minus h once we know the information about f of x. How do we do that? That's an example of a kind that I say the vocabulary of it, the technical matter reference to it, is simultaneous, it has to be, with what happens with graphing of the functions. And I know by my own experience that that often provides or creates challenges for students. In geometry, the notion of a proof. Sometimes you're asking a student to prove something where, especially early on, where it is obvious what it is that is supposed to be proved, and it is very difficult for the student to understand the sense of that, or what does proof really mean. Even in non-geometry places, say if you do baby set theory, you might talk about intersection of two sets is a subset of each of those sets. Well, that's an obvious thing if you draw a Venn diagram. But if you were to forward an argument for it, the student would be at a loss. Calculus, obviously the notion of limit, the notion of derivative and integral, those are all challenges. And of course, in the graduate mathematics, the relevance of what is done in what they learn is also examples of these challenges that I was referring to in the previous slide, as in learning something and learning its vocabulary all at the same time. I do confess I'm being, again, sketchy here, relying on your experiences. Now, I would like to, I mentioned to you one of the programs that we have is Girl Plus Man. And in this program, we try to reach the students, bring them to the campus, and do some work with them. These girls are maybe grade 4, 5, or 6. They're brought to the campus. We bring about 24 of them or so, and they stay for a week, and they have a lot of activities during the night and during the lunch hour. However, the rest of the day, the other 6, 7 hours of the day, they're exposed to mathematics. And they're exposed to a variety of tiny things that they can absorb and that they become interested in and they play. And I think I'll mention some of those topics in a bit. But here I'm going to show you 3 or 4 slides rather quickly. These are examples of material that in 3rd grade, State of Illinois requires of teachers to impart to their students. The one I've identified in red, coordinate graphing pictures located and playing basically with the Euclidean plane, playing with R2, is some of the things that are introduced in grade 3. I do want to make a point about what the state of Illinois is doing in terms of its requirements, and so I've listed grades 3, 4, 5, and 6, and I've identified in red some of these things that I want to use to make a bit of a claim as I arrive on that slide. So here we have in grade 4, for example, exploring pictographs and bar graphs and coordinate graphs and exploring line graphs. For grade 5, they do data, statistics, all sorts of things that you see here, but they begin to graph functions for the first time. On grade 6, they do and I pause there so you can read. Grade 7 and above, of course, we do Algebra 1 and Algebra 2. And finally, well, I want to actually stop at that. But let me recall for you that at least I mentioned that our formal challenges are these plateaus that in teaching of mathematics we're always meeting every time we start a new chapter, every time we have a new idea. And to impart those in an abstract sense is always difficult. Definitions, I think of how they say linear ordering or partial ordering. If you're in the middle of college course, the whole definition of differentiability, continuity. Continuity is a simple definition, but it is difficult to impart it because the first time around the students come about, they are as underprepared as I have lamented. So this shift from static to dynamics is what I would like to go to. Now, abstraction is one of the problems that we are always having with students. When we try to define a certain notion, we might employ a certain letter, and whether that letter to them indicates or arouses the same understanding that it does for us, obviously is not the case. And the reason is that they are thoroughly distant from abstraction. They are thoroughly finding it difficult what it means to speak of a letter that stands for a statement, or stands for a variable, or stands for a function, or stands for any other object. Symbols standing for objects seem to be a difficult thing for these masses of students who come to university, I confess. Now, by static versus dynamic, here I have some examples for you. In my years of teaching, I think this sort of thing that I'm trying to summarize in this slide is always a challenge. Calculus is designed to speak of motion, of changes. It is that subject. But if I imagine that interpreted in these other examples, I think I always come across. I mentioned to you the penultimate example, f of x to f of x plus c. That always gives a challenge to students in intermediate algebra and beyond. Now, how do we succeed with these things? How do we manage to get our students to understand or be a bit more prepared? I here would like to borrow from the world of mathematical education a couple of models and then talk about something that I intend to be center of my small message to you. The Vangeli Model is something that all education specialists are familiar with. Contextual learning is another concept. And what I am trying to address is immersion in a medium. And I'll try to explain what that means. But first, let me talk about, well, I'll let you read again what Vangeli Model is. Caroline, I assume these are stock of things that all education people are familiar with, that are imparted.
I think they're familiar with it, they don't know over it.
They don't know it. But Vangeli model is a model that refers to sequential activities and levels. It's rather connected to Piaget's way of thinking of, well, it's too early to learn certain things, and things do take good time. But it is speaking of learning through activity and doing it sequentially, allowing things to mature, allowing curiosity to settle, to be pronounced, to find itself, and success to be met that way. In a bit, I'll drive you through what those levels are and what those sequential activities mean. Chord is another more recent kind of reference to such things. Learning in context, contextual learning, and react is one of the interpretations of it. And these two ways of suggestion for learning for students in K through, certainly K through 8, is the way of education in US. Now, I said to you, I know the day is long, and I want to just refer to some of the slides here that are spelling out what is meant by Vangeli model. These are the levels. So Vangeli model suggests things come in order. You have to develop a vocabulary and watch out for sequential phases. And the phases are, well, they go out to spell that too. I wanted to mention all this to you and show them to you, not really expecting you to pick them up as I go through them, but that it is very well structured and is indeed intended to be, it's well established, well researched, and it is a demonstration of how things work when students absorb it. A couple of references here. Contextual learning is referring to this constructive learning of the subject, constructivism, where the students ask questions. You've seen these dialogues some of our colleagues referred to today, and an example of that was carried out where meaning and understanding is constructed as it goes on. And if you go to that site there, you find out much more about these methods. So those were the couple of ways of schools of thinking about how to go about education. Now, the message I wish to impart is what I had put in the title, which is, you have a medium where the students are allowed to play and express, then curiosity takes place, they ask right questions, and they learn as much as they can, and then perhaps they can be guided to be more effective, more successful, and more curious about everything they do. Now, one of the things that we do in the education of children in Illinois is to hold back the introduction of Euclidean plane and introduce the real line much earlier and play with that extensively before one gets to Euclidean plane. What I am proposing here is that Euclidean plane can be introduced earlier, and it doesn't have to have a reference, as it was mentioned, to the complex numbers, but rather locations and multiplication and addition, and playing with those locations can be pictorially described, and it can be referred to transformation and rotation and the obvious things that you're aware of. The Euclidean plane already allows you to play with a line in both directions, so you absorb it already, and of course it is very easy to physically be modeled. All you have to do is to go into any classroom, and the floor and the tiling on it allows the students to play with a sense of direction with these axes and learn about the Euclidean plane. And while there, the notion of functions also can easily be understood. So I'm making this observation and the suggestion that we mustn't hold back in, or that we should reconsider the idea of introducing the timing of the introduction of the Euclidean plane into the fabric of education. The argument that I wish to put forward, and I do, of course, again believe that it requires to be researched more formally than I'm ready to report today, but it is important to provide for students opportunities to absorb these conceptual ideas, neither through authority, rote method is good for you, nor at the same time that they're learning the technical stuff, the symbolic stuff, but rather, I'll come to that, but we do this sort of thing in many experiences. We learn how to speak before we write. We learn how to reason before formally investigate. We learn how to be wrong before realizing that there's a distinction between right and wrong. So what I'm suggesting is that these things that I'm saying we learn, we do not do them by the methods that I have put up on the first paragraph, by authority or by simply technical stuff. If the students are allowed to play, as again later a conversation during lunch was reminding me, then more automatically they learn about certain things that prepares them for learning mathematics. I think at our childhood, certainly mine, the notion of playing various games and various puzzles and challenges before us was motivating and at the same time sharpening my ability or my own interest in some of the subjects that I later became comfortable with. At the present time, the impossible number of visual signals and visual introduction and visual saturation of whatever happens around the child prevents the child from being familiar with those logical things or those numerical things that we did. I don't believe anybody plays Monopoly anymore or as much as they did before. If they did, I think video games have taken over. I certainly don't believe that people play backgammon and chess and games that did teach us or made us curious about how to reason or how to evaluate things. I have a class where I talk about, it's a third-year class, and when I talk about a deck of cards, I have to explain how many cards there are in a deck and what the cards are called. The students no longer seem to have played games anymore. And I think my claim here is that when we did play games, which were kind of small spheres of some sort of knowledge, we were immersed into something, we played, we experimented, we were wrong, we were right, and we learned quite a bit from that. And I think that is not as present as it used to. Perhaps we could do something about it. Now, I'm about to give you my opinions. Of course, we must tell them that whatever we suggest is good for them. We must follow disciplined curricular instruction. The state tells us what to do, and we can't entirely avoid them. But let's do it with playful imagery into new media, landscapes and plateaus. Let's just stress abstraction and do that early on. That's what I would tell my audiences of K through 12, if I would, and I have explained this to them. Why don't you read this? I was unfamiliar with papers until just a few days ago, and 3 of those I found out that the kind of thinking that soothes me is at least manifestable, is connectable perhaps with because I put the question mark that I haven't discussed this with Carolyn and her co-workers, but the idea of having environments to have support for students and to have dialogue with students, to indeed promote the idea of independent thinking and curiosity seems to be present all over the place. Let me show you a quick detour. When I was working with my own children, and I wanted to teach my daughter what was the difference between f of x and f of x minus c, I exploited a software which was on the Mac and showed her how conics could be shifting if we played by adding or subtracting something. And just as exercise in play, we did things like this and tried to actually have a whole bunch of conics that managed to draw a given caricature of something. That's another example. But this, of course, was a bit too dry, and it was only my my daughter who was much more keen. But it still is a medium. Why polynomiography? Well, polynomials to functions are the same as atoms to molecules, the same as alphabet to words. They're critical in approximating critical functions, and they're essentially alphabet of higher mathematics. So it's important to introduce those. We could introduce them as early as possible. Why roots? Because children are always asking, when is it the right time to do this or that? That is really translating to so my conclusion and the position I wish to present is that learning about polynomials and the roots should be a rudimentary element, and whenever we can, we should provide a platform for introduction to polynomials. And polynomiography does indeed do that. It's centered on polynomials. It introduces new ideas in Euclidean plane. It can introduce the notion of function. It allows abstraction. It's a place to play. It's a place to raise questions. Now, we did this for those girls that I mentioned to you, 4th through 6th graders, and there's a website that they enjoyed it immensely. They were very creative. They were very ready to own something, to own their own polynomials, to own their own artwork, to become curious, to have something that they would have a basis to talk to their neighbor with. That element of ownership of what they had done, that unique site that they had found, made them far more curious and ready to be perhaps taught something at their level. Now, with those girls, for example, something that we do, we have done this in WIU for the past 3 years. Bahman has been there and visited, and the girls have been extremely receptive. One of the ways of ownership is I put the alphabet for them, assign the numbers 1 through 26 to these, and say anyone's name is associated with a polynomial. So, for example, Amy would be z to the 1, m is 12, m is 13, z to the 13, and y is 25, z to the 25. Write them in order, put plus or minus, and add a minus 1 to the end. So that would be a polynomial. Then they would put that into this software and would become curious as what is their polynomial, look at the right places, draw their own, and become interested in learning. As a tribute to the organizers of this workshop, I took the liberty to do the same thing with their names. This is for Bahman. This is for Dirk. Helaman.
I object.
This is for Radmila. I'll hear later why you object. And of course, I couldn't avoid Carol. The point was that when the students did these things, they became curious, they became playful, they expressed. And meanwhile, subliminally, we taught them something.
Great. Ask the next speaker to start preparations here, while there will be questions for Mr. Kalantari. Any questions for Professor Kalantari?